So today I'll be evaluating 3 different methods for estimating reflection slopes in seismic images. But first, why do we care to do these types of evaluations, and why do we care to accurately estimate slopes in an image? Well, oftentimes these slope values are used as inputs to other image-enhancing processes and filters, such as the one displayed here, in which my colleague Xinming Wu automatically extracts horizon volumes by estimating seismic normal vectors. And a little bit later in my presentation, I'll show you how estimating seismic normal vectors are equivalent to estimating slopes in an image. And I mentioned that I'll be evaluating 3 different methods. The first 2 methods are the most commonly used methods in industry today, and those being the structure tensor method and the plane wave destructor method. The third method will be introduced by me and Dave, uses smooth dynamic warping to estimate slopes. And before I begin this evaluation, let's take a look at how each of these different methods estimate slopes in a seismic image. So we'll start by taking a look at this real seismic data set taken from near offset data in the Gulf of Mexico. And let's take a zoom into the area highlighted by the red box here. Now a little bit later in my presentation it'll become apparent why I chose this particular area to zoom into. So for the structure tensor method, we start by computing structure tensors for every sample in the image. And from these structure tensors, we can compute an eigenvalue decomposition to obtain eigenvectors normal to structure and eigenvectors parallel to structure. And from the components of either the normal vector or the parallel vector, we can compute the slope. And in practice, it just so happens that we use the normal vector to compute these slopes. We then move on to the next sample and do the same thing. And this is what an image of estimated slope values looks like overlaid on top of the seismic data. Seismic image, I should say. Okay, so let's shift gears a little bit. Let's remove the slope image, and let's take a look at how the plane wave destructor method estimates slopes in an image. The plane wave destructor method takes a Gauss-Newton approach to solving a nonlinear minimization problem for slope updates. And we do this by starting with and we do this iteratively for a user-specified number of iterations. We start off with an initial slope image, and the default slope image in the Madagascar software package is an initial slope value equal to 0. And from there, we iterate a number of times until we achieve or converge to the slope image that we desire. And in this case, we do 5 nonlinear iterations, and this again being the default in the Madagascar software package. Okay, so before I begin describing how the smooth dynamic warping method estimates slopes, let's take a look at a couple of shortcomings between the previous 2 methods beyond what was presented at last year's meeting. So once again, let's take a look at this Gulf of Mexico image, our favorite Gulf of Mexico image, and zoom into the same area that we zoomed in before. So once again, for the structure tensor method, we estimate structure tensors for every sample in the image so that we can do an eigenvalue decomposition to obtain eigenvectors normal and parallel to structural features in the image. Eigenvectors normal to structure in the image correspond to the the largest eigenvalue in the eigenvalue decomposition, and the parallel eigenvectors correspond to the smallest eigenvalue in the eigenvalue decomposition. And in areas where we have coherent reflections, such as the area where I've estimated the normal and parallel vectors here, it's fairly easy to estimate these vectors. And these eigenvalues are very far apart, the values. If I move just 7 samples to the right, we have hardly any difference in the orientation between these 2 vectors. But if I move another 7 samples to the right, we have a flip in the orientation between these vectors. And if I move just 1 sample to the right of that, we have a discontinuous flip in orientation. And so I'll flip back and forth between the 2 for you. Now this discontinuity, or this flip in orientation, is caused because in this area, the eigenvalues are very close together. In other words, if we try to distinguish structure in this part of the image, we'd have a very difficult time to do so. If I asked you to tell me what the slope was there, you'd have a difficult time as well as I would. So these smallest and largest eigenvectors very close together, which means that this normal and parallel naming convention is sort of arbitrary in this noisy less resolved region. And this is what this discontinuity looks like in the slope image. And I'll zoom into the same area here. And it looks like where we go from the largest specified, or the maximum specified slope value immediately to the minimum specified slope value. And the reason why I bring up these discontinuities is because they can wreak havoc on a lot of the processes, for example, the one that I showed earlier in my presentation, and a lot of the processes that Xinming Wu uses. The plane wave destructor method aims to minimize this discontinuity by not only minimizing the prediction error, but also including a regularization term, in which we minimize the roughness in the slope update. In other words, we want a smooth slope update. However, I need to emphasize that this minimization of the roughness is on the slope update, which means if we were to supply the plane wave destructor method with an initial model or initial slope value that contained discontinuities, say the output from the structure tensor method, these discontinuities would remain because the smoothness only occurs for the slope update and not the slope image itself. So this brings me to the smooth dynamic warping method. Dynamic warping aims to find shifts between two images such that the shifts applied to one image well approximate the other image. And to show you how we use dynamic warping to estimate slopes, let me show you once again our Gulf of Mexico image. However, this time let's zoom into a different part of the image, here highlighted in red. And let's call this image F. So if we want to estimate slopes for an image F, we first need to compute an image G. And this image G is a one trace shifted version of image F. So if I flip back and forth between the two, image F, G, F, G, you can see in fact it is a one trace shifted version of F. Now if I take a look at image F and zoom into the two traces here highlighted in red, let's get a better understanding of how we actually estimate these slopes and what the process is for dynamic warping. So we start by computing errors for every sample in the trace on the left for a range of samples in the trace on the right. And the fact that we are only looking at a range of samples on the right means that we're constraining the maximum and minimum shifts, or in our case, slopes. And I'm sorry, I forgot to mention that when we do the warping between images F and G, we're essentially warping every trace with the trace adjacent to it. And so the outputted shifts that we get from dynamic warping are equivalent to our slopes. So once again, we take a look at every sample for the trace on the left, and we compute errors for a range of samples in the trace on the right. And as I mentioned, this range of errors, this range of samples that we're looking at allows us to constrain the maximum and minimum shift or slope values. And we do this until we get to the very bottom of the trace. Now once we have our image of computed errors, we can now estimate shifts. And we do so by only looking at specific samples in the trace on the right. So in this case, we're only looking at samples with the same index value or plus or minus 1 index. And this constraint puts, this aspect puts a constraint on the amount that the slope can change as we go from sample to sample, which prevents the type of discontinuities that we saw in the previous two methods. And we do this all the way up until we have our computed image of shifts or slopes. Okay, so now we have three different methods. We have a method that computes slopes based on the structure of the image, a method that takes an inversion approach at estimating slopes, and a method that that estimates shifts to estimate slopes in an image. So let's take a look at 2D slope estimates and see how these different methods compare. So we'll start by taking a look at this synthetic image that I showed at last year's meeting, in which we know the exact slope value everywhere in the image. Not only that, but this image shows a lot of complex seismic or geologic features, such as the ones highlighted here in red, where we have unconformities and faults. And as we go from the upper left-hand corner of the image to the lower right-hand corner of the image, we're increasing in slope value. So once again, I mentioned that we know the exact slope value everywhere in the image, so we can compute different values such as RMS error to analyze the accuracy of these different methods. And once again, I'd like for you to note the sharp discontinuities at the unconformity and at the fault here. Okay, Okay, so the estimated slopes using the structure tensor method shows smoothing across this fault and across this unconformity here. We get similar results with the plane wave destructor method, and if I flip back and forth between the two just quickly, structure tensor method, plane wave destructor, they're very similar, as is the case for the smooth dynamic warping method. But once again, we still have smoothing across the unconformities and across the faults. Plane wave destructor, smooth dynamic warping. Okay, so if I adjust the color bar here, we notice that the upper portion of the image is not in fact a large region of zero slope value. But just below the first unconformity, we can see that we have a constant non-zero slope value. So if we take a look at the estimated slopes here, now the smoothing across the unconformity becomes a lot more apparent. And this is for the structure tensor method here. But just above that unconformity, we seem to estimate slopes fairly well. However, once again, once we get to the faulted area, we see that we are incorrectly estimating higher slope values in the upper portion of that image. The same holds true for the plane wave destructor method. However, just above the smoothing, above the unconformity, we have some slope artifacts here. And we see similar artifacts across the fault in the upper portion of the image. For the smooth dynamic warping method, once again, we have smoothing across the unconformity, and we have similar errors just above that as compared to the plane wave destructor method. However, for the faulted region just in the upper portion, we don't see the same artifacts. So it's very important that I point out an aspect that I hadn't thought about until it was pointed out in one of my rehearsals that has to do with discontinuities. So earlier in my presentation, I mentioned that we would like to mitigate or remove the amount of discontinuities we have in slopes. Well, this is only the case if these discontinuities are caused by noise or low resolved areas of the image. If the discontinuity is in fact caused by a discontinuity in the image, such as a fault or an unconformity, then that would be desirable, and we'd like to have that be the case. And it looks as though the smooth dynamic warping method does that fairly well. Okay, so for time purposes, I'm only showing you the results for a noise to signal ratio equal to 0, but in fact I have synthetic images with higher amounts of noise, noise to signal ratio equal to 1/2 and 1. And for these varying different noise to signal ratios, I can compute an RMS error curve for each of the three different methods. And what we notice is that the smooth dynamic warping method, or curve, lies between the two structure tensor curve and the plane wave destructor curve, at least for the lower noise to signal ratios. As we get to the higher noise to signal ratios, the smooth dynamic warping curve tends toward the plane wave destructor curve, and for the highest amount of noise to signal ratios, produces a higher amount of error than the plane wave destructor method. Not only that, but we can also do a test to be sure that each of these different methods are not producing biases to estimating positive versus negative slope values. So here we have a mean error curve. And we'd like to see that these mean error curves oscillate around the 0 value. This would mean that we have no bias in the slopes that we estimate. However, you'll notice that for all three curves, we have mean error values that are all positive. This would suggest that we do have a bias. However, this bias can occur for if we have higher amounts of positive or negative slopes in the image. So what we can do is we can flip the image horizontally and compute the same mean error curves to see if we have all negative mean errors. And I will not show that curve, those curves here today, but that is in fact the case. So we can rest easy knowing that these different methods, at least for this test, do not have a bias for estimating positive versus negative slope values. Okay, so now that we've taken a look at these different methods for 2D estimates, let's take a look at the comparison for 3D estimates. And we'll do so by looking at the image displayed here, the Teapot Dome data, courtesy of the Rocky Mountain Oilfield Testing Center. Now, since this is a real seismic image, we do not know the exact slope value everywhere in the image. So what we can do is look at these different methods and see how they compare with their slope estimates at interesting areas in the image. For example, we can look at areas here highlighted by the red circle in the inline where we have moderate strength reflectors with noise to the right. This region in the inline where we have steep sloping reflectors with rapid change to the right and noise to the left. area highlighted here in the cross line, in which we have discontinuous reflectors, possibly caused by faults, and an area here in the cross line where we have 2 or 3 strong reflectors located in a fair amount of noise. Okay, so before I continue, I'd like to make a very important distinction between inline and cross-line slopes. So the difference between computing slopes in 2D and computing slopes in 3D is that each of these different methods are now going to produce 2 different slope volumes, one for inline slopes and one for cross-line slopes. And it's important to make this distinction because if we take a look at slope values overlaid on structure in the opposite slice, for example, here we have inline slopes, and if we look at the area highlighted by the red box here in the cross line, we notice that where we should expect to see warm colors or positive slopes, in other words, slopes for features that slope from the upper left to the lower right, we instead see cool or negative slope values. This is because we are estimating slopes in the inline direction. So the slopes that you see here correspond to that direction. The same holds true for the cross-line slopes. So if we take a look at an area of the image here in the inline, we'll notice that once again we have a disagreement in what the slope value that is apparent from the seismic versus what the slope value is showing that is overlaid on top of the seismic. Okay, so not only that can we do this comparison between these 3 different methods, but we can introduce a 4th method, which is myself estimating slopes by hand. And we can see how the different automated slope estimation methods compare to a human. And we see that for the structure tensor method, we estimate fairly similar slope values. And keep in mind, I only showed 4 different examples of picks that I chose to estimate slopes. However, in reality, I have 20 different areas. And these 20 different areas, I tried to vary the strength of the reflectors, the steepness of the reflectors, so I have shallow and steep. I took a look at areas that had a high amount of noise, areas with low amount of noise, and so on. And so I tried to get as much variability in these 20 different samples as I could. And if we continue with the plane wave destructor method, we also have very similar slope results. And the same holds true for the smooth dynamic warping method. But maybe a better way to visualize this image is to compute a mean between these 4 different slope estimates and subtract each of the estimated slopes for each of the different methods and take a look at what the variability is there. So here we have a maximum and minimum slope differences of 0.2 and minus 0.2. And so to first start, let's take a look at what it means to have a slope difference highlighted here by the red ellipse for a slope value not quite equal to 0.1. So here are the estimated inline slopes here for the structure tensor method, and I'd like for you to keep your eye on the area highlighted by the red circle. Now if I move here to the plane wave destructor method, smooth dynamic warping, plane wave destructor, structure tensor, we really don't get much by looking at the colors change and try to see the significant differences by our eyes. So instead what we can do is strip the slope images from atop the seismic and zoom into the area of interest. And now I can represent each of these different slope values at the specific sample here highlighted by the cyan dot by line segments. So here I have a line segment that represents the slope that I estimated by hand. And if I move to the structure tensor method, we see it's a slightly shallower estimated slope. If I move to the plane wave destructor, it's a slightly steeper. You have to look very closely to see this difference. And if I move to the smooth dynamic warping, it is also slightly steeper. Okay, so now we see that these differences in slope are very minor. And for each of these different methods, we could reasonably say that each of them estimated the slope very well. So let's take a look at what it means to have a slope error much larger and much closer to the 0.2 and minus 0.2 maximums. So once again, let's take a look at the area highlighted in red. And once again, that doesn't do us much good, so let's go ahead and remove the slope image and zoom into the area of interest. So now for the sample highlighted by the cyan dot, we'll once again take a look at these line segments. And so even for large amounts of error, if I flip between the different methods, I'm sorry, not amount of error, this large amount of slope differences, we see that there's hardly any variation between the different methods. And I'll flip back and forth between them. So this is main, structure tensor, plane wave destructor, smooth dynamic warping. So in summary, we notice that looking at a real seismic image and trying to do this type of comparison really only lends itself as a proponent for the types of analysis that I did for the 2D. So continuing on in my research, I'll be doing the similar type of analysis in the 2D with a 3D synthetic seismic image, perhaps the one shown earlier by Xinming Wu, in which I know the exact inline and crossline slopes for every sample in the image. Other expectations that we can expect to see between the different methods for Ural data, which is probably the most important question to answer, is that if you're looking to minimize or prevent having discontinuities in slope, say because you're using these slope values as inputs to other image enhancing processes and filters, then you'd probably be better off with a hard constraint on this discontinuity, which is the smooth dynamic warping method. However, if you're looking for an extremely fast method, you'd want to use the structure tensor method. And these are all details that will be you all will be able to find in my thesis, and you all can talk with me later as well. And with that, I'd like to thank you for your attention, and I'm open for questions.